So now that we've found the Jacobian matrix, what we're going to do is we're going to use it to analyze the behavior of these systems of differential equations in two variables. Okay? So what we're going to do is we're going to take our Jacobian matrix, we're going to plug in our equilibrium points. So at a particular equilibrium, we're going to plug those in. Just like when we were in one dimension, we took the derivative of the function and then we plugged in the value of our fixed point, right? Same thing here. We plug in the equilibrium point, we get a matrix. That matrix is going to have eigenvalues. So since it's a 2 by 2 matrix, it'll have two eigenvalues. And that's what we're going to look at to decide what the behavior is like. Okay? So let me go ahead and show you one example, or a couple examples of some of the simpler kinds of behavior, and then I'll give you a classification so that you can look at the eigenvalues and see what the behavior looks like. Okay? So our first example, so what I'm going to do is I'm going to look at some, I'm going to make really easy situations. So we're going to start off looking at dx dt equals 2x, dy dt equals 2y, or let's say equals y. Okay? Dx dt equals 2x, dy dt equals 2y. If you take the Jacobian matrix here, the derivatives here are really simple. So the derivative of 2x with respect to x is 2, with respect to y is 0. Derivative of y with respect to x is 0, with respect to y is 1. Okay? And so a nice thing about this particular matrix is that if you've got a 2 by 2 matrix where the elements that aren't on the diagonal, these two are zeros, the eigenvalues are just going to be these numbers. Okay, so in this situation, our eigenvalues, lambda 1 equals 2, lambda 2 equals 1. Those are the two eigenvalues of this matrix because it's diagonal. Okay, so nice and simple. And the behavior is also very simple. If you think about what the equilibrium of this system is, well, it's going to be where 2x is equal to 0 and y is equal to 0. Well, that nullcline is x equals 0. This nullcline is y equals 0. And so our equilibrium is smack in the middle at 0, 0. Okay, so we have an equilibrium, a fixed point at 0, 0, because this is such a simple system. And if you look at what happens on these nullclines, when you're on the x nullcline, x equals 0, so on the x nullcline, there's no horizontal motion, it's just vertical. If y is greater than 0, dy dt is going to be greater than 0. And so up here you get this. Down here, y is less than 0, so dy dt is less than 0, so we decrease vertically. Similarly, on the x-axis, which is the y nullcline, we only get horizontal motion. And if you look at what that is, when x is greater than 0, it's increasing. When x is less than 0, it's decreasing. Okay? So you can see here, all of the arrows are going out from 0, 0. So this is an example of what we call a source. This is the analogy of an unstable equilibrium in one dimension. If you start at any point not at 0, 0, so right at 0, 0, you're fixed. But if you start anywhere close to 0, 0, you're going to increase out, right? You're going to kind of spread out away from that point, okay? And so this might be like something like a population where both x and y are growing exponentially. So in fact, if you solve this system, it's really easy to solve. You would get exponential growth, x equals e to the 2t, y equals e to the t is the solution. You can see that really easily. And so this is growing exponentially away from 0. Okay? So that's a source. If we take this same system, though, and change everything by a negative. So say this is negative 2x and negative y instead. Our Jacobian is now going to be negative 2, 0, 0, negative 1. Our eigenvalues are -2 and -1. Now both eigenvalues are negative rather than both being positive like they were before. And if you look at your nullclines, which are the same, the behavior has now changed. So if you take your nullclines and you look along the x nullcline, where we have vertical motion, now if y is greater than 0, dy dt is less than 0. dy dt is negative, and so when y is greater than 0, we're going to decrease. When y is less than 0, we're going to increase. Okay? Similarly, if you look along the y nullcline, you get motion like this. Okay? And so now, if you start anywhere in the entire plane, it's going to decrease down to 0. So this is exponential decay, right? We're exponentially decaying into that equilibrium. We call this a sink. Okay, so a sink where both eigenvalues are negative and all of our trajectories, anywhere we start, we're going to decay down to that 0, 0 point. Okay? So that's a sink. What about the third situation that you can kind of think of? What if one of these were negative and the other one were positive? Okay? So if we take our situation and let's say we've got dx dt equals -2x, dy dt equals positive y, that's going to change all of this. So now -2, 0, 0, 1. Our eigenvalues are -2 and 1. Our nullclines are still the same, right? We still have the same nullclines, x equals 0, y equals 0. But if you look at the behavior on those nullclines, now something interesting happens. So along the x nullcline, when y is greater than 0, we get increasing. When y is less than 0, dy dt is negative, and so it goes down. Along the y nullcline, when x is positive, dx dt is negative. When x is negative, dx dt is positive, and it increases in. And so we get this situation. This we talked about last class. This is called a saddle. So when one eigenvalue is negative and the other one is positive, we get a saddle. And you can see if you think about starting anywhere but 0 and kind of following these arrows, what you're going to get is trajectories that look like this. So they're going to follow these kinds of hyperbolic paths. They're never going to actually get close to 0, 0. So this is kind of like an unstable equilibrium, but they're not exploding out like they are in a source. Okay? So that's what I was saying about how in 2 dimensions, there's more complicated things, right? In 1 dimension, either we collapse down to the equilibrium, we approach that value, or we went away from it. Here, we can approach it, we can go away from it, or we can kind of approach it in one direction and go away from it in the other direction. So one interesting thing about a saddle is that if you start here on the y nullcline, you will decay down to 0, 0. Okay? So there is a path. If your y variable is 0 and your x variable is a number, then you will decay down to 0, 0. Okay? And so we'll talk about this when we look at the predator-prey model in the next video. Okay? So let's talk about the complete classification. So these are actually the 3 cases that can happen when lambda 1 and lambda 2 are both real. Okay? Now, lambda 1 and lambda 2 can also be complex, and so I'll write the situations down, what happens then as well. Okay? So let's go ahead and list these all. So lambda 1, lambda 2, both real numbers. So if they're both positive, so if we've got lambda 1 and lambda 2 are both positive, we have a source, right? And so that's where all of the arrows on your null clines are going to be pointing out from the point where you are, okay? If they're both negative, we have a sink. And so all of your null clines are going to point in toward where you're starting. If one is positive and the other one is negative, we have a saddle. And so in a saddle, you're going to get this out in one direction, in another direction. And so these kinds of hyperbolic paths going out. Okay? So those are the three situations where it's real. When it's complex, there are also going to be three different situations. So let's look at what happens when the eigenvalues are complex. So say lambda 1 and lambda 2 are complex, a plus bi, right? Okay? So what happens here just depends on whether a is positive or negative, whether the real part is a positive number or a negative. So remember, for complex eigenvalues, or actually maybe I haven't told you this, eigenvalues come from roots of a polynomial. And so if you've got two complex eigenvalues, they'll always be of the form a plus or minus bi. Okay? So again, you'll talk about that in linear algebra, probably in differential equations, so I'm not going to go into it. But so the imaginary part, you've always got plus or minus bi. And so that doesn't actually end up mattering as much. What's going to matter is whether this real part, a, is positive or negative. And so there are three situations. So either a is greater than 0 for both of them, a is less than 0 for both of them, or a is equal to 0 for both of them. Okay? If a is greater than 0, this is similar to a source in that since a is positive, we're increasing away from our equilibrium. And in fact, we get what's called a spiral source. Okay? And so what that means, your null clines are going to look similar to the way that they do in a source. Okay? But because of the way that your null clines are arranged, you'll get something like this. And what happens is that you spiral out away from your equilibrium point. So again, it's like a source, but we're going to spiral out away. Okay? Similarly, for a less than 0, we get what's called a spiral sink. The null clines are going to look exactly the same, but we're going to decay in toward 0, toward our equilibrium as we go along, right? So the null clines will look exactly the same. You can't tell the difference from the null clines, but what will happen in terms of behavior is that you sink in toward the equilibrium point rather than spiraling out away from it. Okay? So again, stable behavior in the case of a sink, unstable behavior in the case of a source. And so knowing the eigenvalues tells you in advance whether you can expect to decay to that equilibrium or go away from it. Okay? The last one of these, where a is equal to 0, so this is when our eigenvalues are pure imaginary. So if a is equal to 0, we've just got plus or minus bi. This is actually interesting because we get what's called a center. Okay? Null clines will look very similar to what they did in all of these cases. So in all of the complex cases, your null clines look something like this. But what happens in a center is you get stable cycles. So you get trajectories that look like this, where they just kind of keep following the same path. And this is what we see in the predator-prey model, actually. So we'll talk about that model in the next lecture and how we get that, this situation. Okay? So those are the 6 possibilities. So if both eigenvalues of the Jacobian at equilibrium are real, you've either got a source if they're both positive, a sink if they're both negative, or a saddle if their signs are different. If they're both complex, you either have a spiral source, a spiral sink, or a center. Okay? And that's the different possible behaviors of these equilibrium points. We'll do an example in the next video so you can see how this looks for the predator-prey model.